In this video, I want to describe the water vapor saturation curve diagram, which is the foundation of understanding how precipitation forms. So I've shown two versions of the diagram here. On the left is the version in terms of partial pressure of water vapor, and on the right is the version in terms of the specific humidity. Remember, both of these are ways of describing the water vapor content of air. And I'm going to focus more on the one on the right, but I want to show that they basically have exactly the same form, which is, and this is the most important part, that this line here, which represents the maximum amount of water vapor that can in theory be dissolved in air, or saturation, this saturation curve, the level of saturation either measured by partial pressure or specific humidity, increases with temperature. That's the absolute key thing about this diagram. At higher temperatures, you can dissolve more water vapor in the air. That's what this graph shows. So once again, this line here represents the saturation. So I'm just going to label that saturation. Oops, I have the wrong. Let me try here. This is saturation. So that's saturation. And what we mean by that is that represents the maximum amount of water vapor that in theory can be stored in the air. Any more than that, and that's more than the air can carry, and it would have to come out as precipitation. So remember though, however, that we talked earlier about the fact that air can actually contain more water vapor than it theoretically can hold if there's no way for that water vapor to physically precipitate out, because there may be energy barriers to, for example, homogeneous nucleation. So it's possible that air masses can exist within this region over here. I'm going to color it yellow here. This is the region of oversaturation. So the air in this pink region has more water vapor than in theory it can hold. And the reason it has it is because it can't find a way to actually get rid of that water vapor by forming liquid water via precipitation. Now, if there is a way for that to happen, then of course it will shed that water and go back to the line. So the line represents saturation. The pink region represents, let's label that, this is oversaturation. And I'm doing it here on the left. The same thing applies to the graph on the right, where we measure water vapor concentration in terms of its mass. And then below the line here, we'll do that in some shade of blue here, this represents the state of undersaturation. So down here, the air contains less water vapor than it can in theory carry. It could carry more. So whatever, if the air mass plots down here in the blue region, then it is undersaturated. Boy, that's terrible. Let's try that one again. Undersaturation with respect to water vapor. And the same thing again applies to the graph on the right, just measuring the water vapor concentration in a different way. Now, let's take a look in a little bit more detail about how this works. I'm showing here the diagram that we more commonly use, which is the specific humidity. Remember, an advantage of this is that when we look at specific humidity, it doesn't change as the air mass either expands or contracts, and that wouldn't be true of the partial pressures or of the absolute humidity, which is based on mass per volume. So this is mass per mass, so this is insensitive to changing the volume of the air, and that's why we like to use it when we're thinking about air masses that go up and down and expand and contract. So let's think about what happens if we start with let's just pick an air mass. So here's a point here, that any air mass can be plotted on this diagram as a point. So let's say I pick a point, an air mass right there. Okay, so this air mass has the two properties given by the axes. It's at a temperature of 25 degrees, right? And it has a specific humidity of 15 grams of water vapor per kilogram of air. And that's where this plots. Any other air mass that I encounter should be able to plot on this diagram. And if it's not super saturated with respect to water vapor, then it will plot in general within the blue region, right, of the diagram, or perhaps on the line if it's fully saturated with water. Now, one of the things we want do is describe the degree to which this air mass, how close is this air mass to being fully saturated with water vapor? And we do that with a concept called relative humidity, RH. I'm just going to abbreviate it, relative humidity, which is defined as, and I'm going to do it here in terms of the specific humidity. So it's the specific humidity, I'll give it the symbol Q here. Q of the air divided by the value of Q at saturation. So in this particular case here, Q of the air, so for this example here, the relative humidity will equal the specific humidity of the air, which is 15 grams per kilogram of water vapor, divided by the value at saturation. So at this temperature, at 25 degrees, if we look on our diagram, this is the value when the air mass is completely saturated with water vapor. Now it's just a little bit below, but I'm going to say close enough to, if we look here, close enough to 20 grams per kilogram. So the saturation value here is 20 grams per kilogram. That's the value we'd get at saturation at that temperature. And so the relative humidity in this case will equal 15 divided by 20, which is 75%. So we would say that this air mass here at the black dot has a relative humidity of 75%. As it draws closer to saturation, the relative humidity will increase. And if I were to ask, for example, what is the relative humidity of an air mass that plots right here on the line? Well, if it's on the line, then its specific humidity and its saturation specific humidity are the same thing. So for this guy here, the relative humidity is equal to 100%. Now, relative humidity is important because it's a good indicator of how we feel in such an air mass. When we get very close to when relative humidity gets very close to 100%, we tend to feel clammy. I mean, if we sweat, for example, there's not much place to put that water on our skin into the air, so it can't evaporate very readily off of our skin, and we sort of feel clammy and sweaty and yucky. On the other hand, if the relative humidity is really low, then water on our skin or in our mouth or on our tongue is rapidly evaporating into the air. The air has so much capacity to absorb that water that we feel very dried out, and sometimes our lips will crack or we'll get a sore throat or something like that. So the relative humidity is actually a really useful concept, and it's a useful concept as well. We'll discover for things like describing evaporation or what kind of how plants will respond to changes in humidity. I want to make a quick point is that even though it's not exactly the same, we can sort of do the same thing to calculate relative humidity using the partial pressure diagram. So remember at 25 degrees, that was what we looked at last time, we found that, remember at 25 degrees we had a relative humidity of 75%. So we could actually plot that air mass on this diagram as well. What we would do is we'd note that, well, at 25 degrees C, saturation, now again, this is in terms of partial pressure, right? The partial pressure at saturation at 25 degrees is about, it's right there, right? So it's about 26, so the partial pressure of H2O, that's how I'll draw it, at saturation is equal to 2,600 pascals. And so if we want to know the partial pressure of our air mass, not at saturation, but our air mass at 75% relative humidity, what we do is we take 75% times 2,600, and that turns out to be, sorry, that's not very clear, is it? It turns out to be at about 1,950 pascals. So on this diagram, the air mass would plot right about, let's do it in black again, right about here, okay? And we could do the same thing. If I gave you an air mass that plotted here, and in other words, if I told you its temperature and partial pressure, you could calculate its relative humidity using the same concepts I described before. Okay, last thing I want to talk about. So let's again take our air mass, and we'll pick the same one that had a relative humidity, there it was, 25 degrees, 15 grams per kilogram. And let's ask, how can we move the plotting position of this air mass on this diagram? So in other words, what would it mean if the air mass here, if the plotting position of the air mass moves to the right or to the left? Well, to the right or left, that's just changes in temperature. So to move right or left, all that means is that we're changing the temperature. Now, we can't move too far to the left, right, unless we're going to have to deal with that saturation curve, right? But we can presumably move all the way we want to the right. If we move to the left, eventually, as we move to the left, we're going to hit the saturation curve, right? And then we're going to have to think about what happens at the saturation curve. Notice one thing that's actually we can read off of this diagram as well. As we move to the left, the relative humidity is increasing, right? It starts out at 75%. By the time we get to the saturation curve, let's draw it at a red dot here. By the time we get to the red dot now, the relative humidity is 100%. So along this red arrow here, the relative humidity is increasing. And similar arguments will show that as we move along, let's call it the green arrow here now, towards higher temperatures, the relative humidity is decreasing because the specific humidity is staying the same, but the specific humidity at saturation is increasing. And since the relative humidity is the ratio of those two things, the denominator is increasing, and so the relative humidity will decrease. So this is decreasing the relative humidity. In the other direction, we are increasing the relative humidity. Okay, now how about moving up or down on this diagram? That's a little bit more tricky. So to move up on this diagram says at the same temperature, we are increasing the specific humidity. We are putting more water vapor into the air. And the way that happens is if the air mass, for example, were to sit over a body of water for a prolonged amount of time. For example, in the oceans, it's sitting over the ocean, water is evaporating off of the ocean and slowly feeding more water vapor into the air. Now that process happens, but it's generally really slow. And for most of the cases we're going to be considering, that's not really a very important process. So in general, we're not really going to think about what happens to air masses that are sitting around long enough over a body of water to where their absolute or specific humidity can increase. So even though this can happen, we're not really that all concerned with it. Now the other direction is probably the most important. How can we get this air mass position to move down? Moving down, remember, means that it's going to contain less water vapor. So how can that happen? Well, the short answer is the only way to make an air mass contain less water vapor is to have some of its water vapor precipitate out. And that only can happen if we were on or beyond the saturation curve. In other words, that can only happen if we are in the super saturation region, or more likely, so anywhere in this pink region here, that can happen. We can cause precipitation, and that will extract water vapor from the air. Or, like I said, more importantly, more commonly actually, as I'll explain, we are on this curve. That red line is supposed to represent we're on the saturation curve. So think about what happens. That's too big. So you get the idea. So think about what happens if I cool this air mass now. I'm going back to cooling, right? And I cross over this line, right? I go over a little bit over this line. This is greatly exaggerated. Let's say I go a degree over this line or half a degree over this line. And let's suppose as well that there are nuclei available that allow precipitation to occur without any barriers. So as soon as I get a tiny amount in the pink region, I immediately form nuclei, or I immediately precipitate out water, and I drive this, then I extract water as rain, and I come right back like this. And then I cool a little bit more, and then immediately form rain like this. And if you can imagine these steps becoming really, really tiny, what actually happens is that in order to, let's do it in kind of blue here, what actually happens is that I will actually ride down this saturation curve like this. If there's no barrier to precipitation, I ride down this precipitation curve shown on the blue line here. So this is driven by a decrease in temperature, but because I reach saturation and then I can't enter the supersaturated region because there's no barrier to the precipitation of liquid water, I ride down that curve, and that is really the only process that allows me to go down on this diagram, that allows an air mass to move to a lower position on this diagram, one that suggests it has less water vapor in it. So it has to happen when it's when it's riding down this curve, which means that decreases in water concentration always go hand in hand with decreases in temperature. That's the way we extract water vapor from air via precipitation, by moving down this vapor saturation curve.